Hello everyone. In this video, we are going to discuss section 6.1, the basics of counting. As you can find here, we have a few counting rules: the product rule, the sum rule, the subtraction rule, the division rule, and then a lot of examples in this section. And now let's move to the board to give an overview. So before we further explain the details and examples of different counting rules, we first need to know what is counting. Right? So in this course, when it comes to counting, so we should know that we have a set that is defined by a specific predicate. I recall that in chapter number 2, a set could be defined as a set of elements in the universal set provided that predicate. So an element is an element belongs to a set S if and only if the predicate X is true. All right, so now with this understanding, so with this predicate, so we can learn about rules, right? One or more rules to describe the behavior of the elements in the set. So the next issue is the objective of counting. Right? The objective counting is very clear, is to find the cardinality of the set. Right? So counting means given a set S with this predicate X is an element in the universal set and Px is the predicate to define, we want to find the cardinality of set S. And so that is the main objective of counting. Right? And certainly this counting is a very important skill and very important issue. And then in many of these counting problems, so we, as I just explained, the main objective is to find the cardinality of the set. But usually in a lot of counting problems, so each element is an arrangement. Each element is an arrangement of some objects, like the arrangement of some bits. For example, if we have 2 bits in a string, so we could write 0, 0, 0, 1, 1, 0, 1, 1. And similarly, we could have this arrangement of the truth value of some propositional variables. Like if we have 2 propositional variables in chapter number 1, we discussed this about the truth table. Right? So to find this, all the combination, all the these truth value combinations, so we know we have to use 2 to the power of n. If we have n variables, then we have 2 to the power of n rows in the truth table. So that is also an example of the arrangement of the truth values. Right? All right, so closely relevant to that, let's say we have counting. The objective is to find the cardinality of the set. And for many counting problems, we are discussing the arrangement of objects. And this area that investigates the arrangement of some objects is called the Combinatorics. Combinatorics is the study of arrangement of objects. And counting is the basic. Right, so here we can consider combinatorics is an application of counting. And from there, from the understanding of the combinatorics, so we also have these relevant proof techniques. Proof techniques about using some counting rules. So there are called combinatorial proof. Combinatorial proof is a proof technique. So this follows a lot of proof techniques we introduced in chapter number 1. And we also have just finished our discussions in chapter number 5 about induction proofs. Right? So combinatorial proof is another proof technique. So the objective of combinatorial proof is to show two numbers are identical. Let's say x equals to y. We want to prove, this. X equals to y. So two methods under this combinatorial proof are relevant to counting in that the first method is called the proof by double counting. Right? So this is to show that the two numbers are actually the cardinality of the same set. Cardinality of the same set. Right? That is to show that x equals to y equals to cardinality of set S. So if we can show that they are the cardinality of the same set, that these two numbers are identical. And usually when we are using this proof technique called double counting rule, so the method that we are using to obtain these x and y could be different. Later on, we are going to explain there are several counting rules like the sum rule, the product rule, the sum rule, subtraction rule, and the division rule. So using different rules and the combination of these rules, we can count the cardinality of the set, or counting the number of objects in a set. If we can show that there are actually different ways to count the cardinality of the same set, so we can then show that these two numbers are identical. The other method is called proof by bijection. Right? So this follows the definition, the second definition of cardinality in chapter number 2. Right? So when we have two sets, the two sets have the same cardinality if and only if there exists a bijective function from set A and set B. Right? So in chapter number 2, so we explain that cardinality of set A equals to cardinality of set B if and only if there exists a function f from A to B. And then this function A to B is bijective. So basically, we are using this rule if we want to prove that two numbers are identical, then we can show these two numbers are the cardinality of two sets. Right? Two numbers. The two numbers, let's say x equals to cardinality of A, and y equals to the cardinality of B, and there exists f from A to B. And then this f A to B is bijective. All right, so those are the relevant issues. And then besides this application of the combinatorics and also combinatorial proof, so we also have these applications of counting discrete probability. So these topics, they are actually covered in chapter number 7. Chapter number 7 in this textbook. So to briefly summarize, so we have just present an overview of counting. First, you have to understand that we are defining a set by using a set builder notation. That means we provide a predicate to specify the feature or the characteristics of elements in the set. And based on this predicate, the objective of counting is to find the cardinality of the set. That is, given predicate, we want to find the cardinality of the set. And then we just also explain several applications, in particular the combinatorics, and also the combinatorial proof under this combinatorics. And another important application of counting is the discrete probability. Right? In this chapter, we are not going to further discuss the discrete probability, but we may cover a little bit, right? Just to do a brief introduction. Like if you are playing some card games using the arrangement, the pattern of the a certain number of cards, so we could use the counting rule to identify the discrete probability. That is the probability of winning a certain card game. All right, so next we are going to move to the counting rules. We are going to start from the first rule called the product rule. The main idea of the product rule is that every element in the set could be created by an algorithm. So here we want to relate the discussions of these counting rules to algorithm. Every element in a set can be created by an algorithm that consists of a sequence of steps. So here I'm using another way to describe the algorithm called the flowchart. So start, step 1, step 2, and then step n and n. Right. So if we have a sequence of steps to create an element, this sequence of steps could be used to create every element in the set. Right? So if we can find this kind of algorithm, so then we could use the product rule. So the total number of elements that in the set, that is the cardinality of set S, is equal to the product of numbers of ways to finish all the steps. Let's say, suppose this first step we have M1 ways. The second step we have N2 ways. And the nth step we have N sub n ways. So the total equals to n1 times n2 times n of step n. So apparently this form is a sequence of products, so that is why this is called a product rule. In the lecture slides, actually you can find a simpler scenario. A procedure can be broken down into a sequence of two tests. Right, two tests. So we have M1 and N2, so the total is M1 times N2. But in general, so we should find a total of n steps, and then each step we have a certain number of ways. So eventually we have the total equals to M1 times N2 and a lot of multiplication all the way to the last number, n sub n. Right? So the total number of elements is equal to the product of number of ways to finish all the steps. And then we are going to use a lot of examples to further explain. So actually, these a lot of these examples we have also briefly explained. Like the first example, how many bit strings with length 7 are there? So for this, we can certainly define an algorithm with 7 steps. A total of 7 steps to choose a sequence of 7 bits. Right? In the first step, we choose the first bit. The second step, we choose the second bit, and the 7th step, we choose the last bit. Right? And apparently, since we are talking about the bit string, right? Bit string, the alphabet is 0, 1, so we can only choose one of these 2 symbols. Right? So in each step, we have 2 choices or 2 ways. So together, we have 2 times 2 times 2. So we have a total of 7, right? 7 2s. This is 2 to the power 7. So which is 128. Right? So that's the first example. You can also find that in the lecture slide. In a very similar way, as I briefly mentioned at the beginning of this video, so when we are constructing the truth table, if we have a total of n propositional variables, so to get all the possible truth value combinations, so we are going to have 2 to the power of n, right? So using almost the same method to count the total number of elements, to total number of these truth value patterns. All right, so the next example is relevant to the license plates of vehicles. Right? So here we want to count the number of license plates that can be created. And more precisely, by using a format. For example, the format of license plates in Puerto Rico is so actually there are several formats. Here we are talking about the most common format. Most common format of license plates in Puerto Rico is that we are going to use 3 English letters followed by 3 decimal digits. So this format is known as format ABC 1, 2, 3. So this is just the name for this type of format. So later on we can find these. There are very similar formats in other states. So then we can define an algorithm with a total of 6 steps, because now you can find there are a total of 6 characters in this license plate. And then in each of the 6 steps, we choose 1 character. In the first 3 steps, we choose 1 English letter, right, in each step. And then in the last 3 steps, we choose 1 decimal digits. All right, so apparently here we have 26 choices in the first step, 26 in the second, and 26 in the third step. And after that, we have 10, 10, 10 for the 4, 5, and 6 step. So multiplying all these numbers together, we add a number 17,576,000. So this is the total number of license plates that could be produced by using this ABC 1, 2, 3 format in Puerto Rico. And considering that the population in Puerto Rico is some number between 3 million to 4 million, and for in the foreseeable future, we can consider that so this format is sufficient in Puerto Rico, right? Because now after counting, we know that the 17 million is a few times more than the population in Puerto Rico. However, if you consider some other states, for example, let me go to this Wikipedia to see this New York State. Right? New York State has a population a little more than 20 million. Right? 20 million is actually larger than these 17 million possible license plates. Right? So therefore, So if you check the format of the license plate in New York, so you're going to find that they are actually using a different format with one more decimal digits. ABC 1234 in New York. And apparently, here the pattern is very similar to the pattern used in Puerto Rico. Puerto Rico is using ABC 123, and New York is using ABC 1234. So if you count or calculate the total number of license plates that can be produced by using this ABC 1234 in New York State, then you can get a number that is 170 million. 175 million 760,000 possible license plates in New York City. All right, so that is the second example. And again, so to briefly review the methods we use in the product rule is that, again, our objective is that we are counting the cardinality, right? We are trying to get the cardinality of the set. And if the predicate shows that every element in a set could be created by an algorithm that consists of a sequence of steps. Right? So in the first example, we have a sequence of 7 steps to create one bit string. And in the second example, we use a sequence of 6 steps to create a license plate number in Puerto Rico. Right? Similarly, you are going to use a total of 7 steps to create a license plate number in license plate pattern in New York State. Right? All right, so I think that is the basic idea and the 2 simple examples. And next, let's see some other, the next 2 examples are relevant to the number of functions. Right? So in problem example number 3, so we are counting the total number of functions, total number of functions f a to b, where the cardinality of set A is m and cardinality of set B is n. Recall that in chapter number 2, right? We claim that we define that a function is a set of order pair, right? A set of order pairs in chapter 2. And we also have other conditions. For every element A in set A, there is a unique pair, AB, in the function. So from this description, so we can understand that in order to specify a function, let's say function is a set of order pairs, right? And then inside the order pair, the first element is unique. And then it must be the, if we combine all the first element in all these order pairs, we are going to get set A. Right? So every element A in set A must have a unique order pair AB. Right? Certainly, so for this number of order pairs is apparently m. Right? So we have m order pairs. And then once we understand this definition of function, so we can move to the analysis, the next step. To specify a function, we can define an algorithm with m steps. I just explained that in a function f from set A to set B, we must have a total of m AB pairs. Right? Since we have m pairs in the function, so we could use m steps to specify every order pair. Right? And in each step, there are certainly n choices because n is the cardinality of set B. Right? There are n choices to choose an element in set B. So here I'm using a simple example. Let's say the cardinality of A is 3, and cardinality of B is 4. So the idea is that, so in step number 1, we choose an order pair, and the first element in the order pair is this element. Let's say this element 1. And after we define this order pair, so in the second step, we choose the mapping for element 2 in ZA. For example, here I can choose in the second step, and in the third step, we could choose a mapping for element 3 in ZA. Right? So we are going to have these 3 steps because the cardinality of A is 3. And then since this function, we don't have other constraints. So each time we choose a mapping for every element in ZA, we have n choices. Right? So the cardinality of B equals to 4. So for these 2 sets, A and B, the number of functions that we can create will be 4 to the power of 3. Because you have 4 choices for the for element 1, and 4 choices for element 2, and 4 choices for element 3. So together we have 4 to the power of 3. Right? So in general, let's move back to the calculation. The total number of functions that we could can create is n times n, and then here we have a total of m numbers, right? So eventually we get this total number, n raised to the power of m. Right? So that is a big number, n raised to the power of m. All right, so just now we have tried to explain this total number of functions that could be created given 2 sets with a certain number of elements in each set, in the domain A and domain B. And in the next example, we are going to add some more constraints. Here, we are again counting the number of functions, but we are counting the number of injective functions, FA to B. Well, A has a cardinality m, and B, the cardinality is n. So these are the same as the previous example. But we need to have another constraint. Is m is less than or equal to n, like in the previous example. So here, cardinality of set A is 3, cardinality of set B is 4. So it is possible to find create some injective function. If this condition is not true, m is greater than n, then we cannot create a bijective function. So similar to the previous example, so we have the function is a set of order pairs AB, FA equals to B. Every element A in set A, there is a unique AB pair in the function. So this pair is an element in the function. And then very importantly, for an injective function, if FA1 equals to FA2, then A1 equals to A2. That basically means that 2 different elements in set A must be mapped to 2 different elements in set B. So this is an important constraint. And then it's going to affect the result of counting. And then to specify a function here, we are using the same algorithm. We use a total of m steps to specify all these m elements, right? M AB pairs. So next we have further explanation. In the first step, there are n choices. Like in the previous example, the first, suppose we want to create a mapping for element 1. So in the first step, we have 4 choices. In the first step, we have 4 choices. However, since we want to create an injective function, so in the second step, we are going to have m minus 1 choices because this function is injective. So you cannot map the second element. For example, in this case, we cannot map this element 2 to the same element in the that has already been chosen in set B. Right? And eventually, in the last step, in the mth step, there are n minus m plus 1 choices. Right? So this is a sequence of numbers, n to n minus 1 to n minus 2, and eventually to m minus m plus 1. So we can simply finding that this total number of steps is m. Okay, so based on this analysis, so we can calculate this total number is n times n minus 1 and all the way to n minus m plus 1. If we are using the product form, we can write this big pi I equals to 0 to m minus 1. And then the expression for numbers in this sequence is n minus I. So certainly the first element in this sequence, when I equals to 0, so this number is n. Right? The last element, when I equals to m minus 1, so we have m minus m plus 1. Right? So this is the product form of the total number. So in the lecture slides, you can also find these discussions. Right? The number of functions is n to the power of m. Remember, this n is the cardinality of the codomain, and m is the cardinality of the domain. And then the number of one-to-one, which is bijective. Number of bijective function is n times n minus 1 times n minus 2, and at the end, n minus m plus 1. Right? So if we want to have an accurate expression for that without some dots, so we should write this product form. Big pi, I from 0 to m minus 1, parentheses m minus I. All right, so in the next example, so we can find this number of telephone numbers. So for this, we first define 3 sets of digits. Right, the first set is straightforward. So the first set is called set x. So it consists of all the decimal digits from 0 to 9. So the cardinality of x is 10. And the second set called y is a set with 2 numbers, 0 and 1. So the cardinality is 2. And the third set has all numbers greater than 1. All the decimal digits greater than 1. So we have from 2 to 9. So the cardinality of set n is 8. So these are the definitions. So we define this here because next we are going to introduce the format of telephone numbers used in the North America. So based on this, we can define an algorithm to specify a sequence of digits in a phone number. More specifically, in North America. So first we have a format called NYX, NNX, XXXX. So this format is used in during the 1960s. So recall that we define this n as a set with numbers from 2 to 9. It's decimal digits greater than 1. So these are the possible choices as the first digit in the telephone number. And the second is y, so we have 2 choices. The third is x, 10 choices. And then n and x, so we have a times 10, right? And at the end, we have x, 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 x. So apparently there are a total of 10 digits in the telephone number. So we can define an algorithm with 10 steps. So we need an algorithm with 10 steps. So once we have that algorithm, as I have just explained in general, you need to identify an algorithm with a sequence of steps. And for this phone number, we have an algorithm with 10 steps. So we could just simply multiply the number of ways to choose each digit. The first number, H is second, 2, third, 10, 4, 8, 5, 8, and 6, 10. So we can then simply multiply all these numbers, right? All these numbers. So we are going to get 1 billion and 24 million. So this is the total number of phone numbers that could be used using this format. And later on, after 1960s, so with the emerging of this telecommunication, so we have more and more requests to install phones for individuals, family, and companies. So people consider that this total number may not be sufficient. So that is why after 1960s, so we are going to we are actually using a different format called NXX, NXX, XXXX. Right? So you can find that in this total of 10 steps, 2 numbers. So we should choose the digit from set N. So we have A and A. The rest, 8 digits, they could be from 0 to 9, so 10 choices. So the total number, so in terms of number, this is quite straightforward. Actually, the previous one is also quite straightforward because you can find that A is 2 to the power 3, right? 2 to the power 3 times 2 to the power 1 times 2 to the power 3 and 2 to the power 3 is 2 to the power 10, is 1024. And then we have 1, 2, 3, 4, 5, 6. So it's 1 billion. And for this, we have A times A is 64, and then 1, 2, 3, 4, 5, 6, 7, 8. Right? 8, 10 is 10 to the power of 8. Right? So we have 6.4 billion numbers. So this is a very big number. It is supposed to be sufficient for a long time. All right, so that is another example how to count the total number of different telephone numbers that could be used in the North America. So the standard is actually the North American numbering plane, NAMP. So these phone numbers covers a lot of regions, starting from the country code 1. The next example is the cardinality of power set, PS. So in chapter number 2, we have already introduced, so for set S with n elements, the cardinality of power set PS equals to 2 to the power of n. And then in chapter 5, so there is a proof by induction. A proof by induction to show the cardinality of power set PS equals to 2 to the power of n. Here we are using this counting rule. Right? So recall that in order to specify a subset, right, so we know that every element in the subset must be an element in set S. Right? So we can define as an algorithm with a total of n steps because the original set S has a total of n elements. So we can define n steps to specify possible elements in the subset. That is, in each step, we specified element in S and decide whether or not it could be included in the subset. So here, you can simply imagine that in all these n elements, all n elements in set S, we can just list them in a sequence. So you have element 1, element 2 to element n. So after listing all these elements, so you define an algorithm with n steps. Right? The first step, we decide whether or not we should include element 1 in the subset. In the second step, we decide whether or not we want to include the second element into the subset. Right? And apparently, after we define this algorithm, we're going to find that we have a total of n steps. And in each step, we have two choices, choosing that element or not choosing that element. So the total number of subsets can then be become by using the product rule. So 2 times 2 times 2. So we have a total of n 2's in this sequence of multiplication. So the total number will be 2 to the power of n. So at this point, you're going to find that the counting of the cardinality of power set PS is very similar to counting the number of bit strings, number of all bit strings with a certain length. And also, it is similar to the case that we want to generate all truth value patterns for n propositional variables. They are all 2 to the power of n. And the last example for the counting rule is the cardinality of the Cartesian product. Right? Cartesian product, let's consider A1, A2 to AM. They are finite sets. Right? Finite sets. So the Cartesian product of these sets, A1 times A2 times all the way to AM. So we should know that by definition, the Cartesian product, right, the element of the Cartesian product is A1, A2 to AN, this smaller than A. So each element here, A1 is an element in set A1, A2 is an element in set A2, and AN is an element in set AN. So together, so this is n tuple, ordered n tuple. So in order to specify this element, which is the n tuple, so we can define an algorithm with n steps because now we have n sets. Right? In the first step, we choose an element from set A1. In the second step, we choose an element from set A2, and so forth. So here I try to simplify that by using this method. In step I, well, I is greater than or equal to 1, less than or equal to n, we choose an element from set AI. So apparently, the total number of elements in the Cartesian product will be the product of cardinalities of all these n sets. Product I from 1 to n, the cardinality of AI. Right, so that is actually also a rule we already introduced, we already explained in chapter number 2. All right, so with that, we have finished the first rule. And then the second rule we are going to discuss is the sum rule. Right? So the main idea is somehow similar to the product rule. The difference is that here we consider that every element in a set, right? Every element in a set can be created by an algorithm that consists of some parallel process. So for that, let me draw this flowchart. Process 1. Process 2. And then eventually process n. So this is the flowchart of this kind of algorithm. And the second bullet is very important. So there is no overlap in each pair of two processes. No overlap. So which basically means that you cannot generate the same element using different process. Let me put this explanation here. An element cannot be generated by two or more process above. So this is very important. Right? So to apply the sum rule, you have to first create an algorithm that has parallel processes. And also you have to make sure that these processes, they don't overlap, which means that you cannot create the same element using different process. So with this condition, so we can consider the number is N1 for process 1, N2 for process 2. And the last step, N sub capital letter N. So the total equals to summation I from 1 to capital letter N, and I. So this is the summation. So that's why we call this sum rule. All right. So these are the important points in the definition. So first, we should be able to use some parallel process to generate every element. And secondly, there's no overlap for any pair of two processes. Right? And thirdly, once we have guaranteed the first 2 points, then the total number of elements equals to the sum of number of ways to finish each process. So the first example for this sum rule is like the selection of representative from some people from the same department. So in the let's consider, for example, in order to resolve the strike issue in the university, so we choose a representative from each department. Right? And considering one department has 37 professors and then 83 students. Right? And the second one is, the second item here is very important. So this is the second rule. There's no overlap in each pair of two processes. Right? So we consider nobody is both professor and student. All right. So in this way, since we want to choose a single representative, so we have two parallel processes. Right? The first process, this is ES. Process P1, we choose a professor, and then process P2, we choose a student. So the total number of ways to choose a representative for that department equals to 37 plus 83 equals to 120. All right, so that is the first example. And then the second one is the cardinality of union, a union of n sets, S1, S2 to Sn. In this sequence of sets, every pair of sets are disjoint. Right? So for I, for j, if I is not j, then Si intersection Sj equals to empty set. Right? So this is the meaning of pairwise disjoint. So with this very important feature, so remember that here, when we define this sum rule, we specify very clearly, so there is no overlap, right? So this is relevant to the requirement. So we have this pairwise disjoint feature of this set, a total of n sets. Right? So in order to find the cardinality of union, so we can define an algorithm to specify an element in the union. Right? Define algorithm to find to identify an element in the union. Right? So this algorithm has a total of n parallel process. In this n parallel process, for process K, we choose an element from set Sk. Right? So you have algorithm to create one element in the union, this algorithm has a total of n parallel processes. And then we can calculate the total number of ways to find this element in the union is the summation, right? S1 plus S2 plus all the way to Sn. So it's a big sigma I from 1 to n, the cardinality of Si. All right, so that is the second example. We can find this here on slide 13. And finally, the number of labels. Right? Here, considering the case that we want to generate a label, and then the label, the valid label, could have two formats. The first one is an English letter, and the second format is one English letter followed by one decimal digit. So we can define an algorithm with two parallel processes. Right? The first process can generate a label using format 1, and the second process can generate a label using format 2. Apparently, the number of ways to go through process 1 is 26, and the number of ways to go through process 2 is 26 times 10. So actually, this is an example that illustrates, so in general, so we can actually combine the product rule and sum rule in different ways. Right? So for this, let's say we have this start, and then two parallel process. Choose one letter, and then choose one letter, and then choose one digit. And so as I just explained, so this is an example that illustrates a combination of the two rules. So we use the product rule in this branch, and then we use the sum rule for the total number of ways to generate a valid label. And also this example, we could have a different algorithm. That is, we are going to have start, choose one letter, and then two parallel branches. Choose nothing. Choose nothing is a step, and then the other one is choose one digit. So if we compare these two algorithms, we're going to find that the algorithm, they are different, right? But they are counting the same set, right? The cardinality of the same set. So this could be an example that we are going to further discuss in the next video about the double counting. So from these two examples, we can find that the first example, we have in the first level, we apply the sum rule. The second level, for the second branch, we use the product rule. But the second algorithm, in the first level, we use the product rule, and in the second level, for the second step, we are using this sum rule. Right? So there are actually many different ways to count the cardinality of the same set. Then based on this very simple observation, so we can utilize the double counting rule, and then this double counting rule could help us to further understand the other counting rules, like the subtraction rule and the division rule. So we are going to use another video to discuss the remaining rules and examples in section 1.